So you've probably seen those incredible pictures, right? The northern lights. And you just have to wonder, what is actually going on up there? How does our little planet cook up one of the most amazing light shows in the entire solar system?
I mean, look at that, these shimmering curtains of light. They just dance across the sky. It looks like pure magic. But you know what? It's not magic at all. It's physics. Just on this epic, cosmic scale. So that leads to the big question. What's the secret recipe?
All right, let's figure this out. We're going to break down the whole cosmic recipe. It really comes down to 3 key ingredients, starting with a stormy star all the way over 93 million miles away and ending right here in the very air we breathe.
You know, for centuries, people came up with some amazing stories to explain this. In Norse mythology, it was the light reflecting off the Valkyrie's armor. Some Inuit cultures saw it as spirits of the dead playing a game. Incredible stories, but these days, science gives us a totally different but just as amazing answer. And it all kicks off with charged particles from our sun.
So, ingredient number 1. It comes from the very heart of our solar system, the sun. And we have to get this idea out of our heads that the sun is just this calm, steady ball of light. Nope, it's an active, incredibly stormy star, and it's constantly blasting material out into space.
And that material? It's called the solar wind. The best way to think about it is like a constant wind of superheated plasma. We're talking mainly electrons and protons just streaming away from the sun. And just like wind on Earth, sometimes it's a gentle breeze, but other times it's a full-on gale.
And yeah, when I say wind, I'm not talking about a nice summer breeze. This stream of particles is absolutely blazing through space. We're talking speeds around 1.5 million kilometers per hour. Just let that sink in for a second. That's the energy that's going to eventually power this whole light show.
Okay, so we've got our first ingredient, this super fast jet of solar particles. Now we need ingredient number 2, a target, a planet for it to hit. But here's the thing about Earth. It doesn't just sit there and take the hit. Oh no, it has its own defense system.
And that defense system is called the magnetosphere. It's generated by the churning molten iron deep inside our planet's core, and it creates this invisible force field. It literally wraps around the entire Earth, and its main job is to deflect almost all of that incoming solar wind. Pretty cool, right?
And you can see just what a beating the shield takes. That solar wind physically slams into it. It squishes the magnetic field on the side facing the sun and then stretches it way out into this long tail on the night side. So our planet's protective field is constantly being pushed around and warped by this relentless solar onslaught.
But here's the twist. The shield isn't perfect. It has a couple of weak spots. You see how the magnetic field lines all curve back and dive right down into the planet at the north and south poles? Well, that creates a perfect funnel. It's like an open door, guiding some of those solar wind particles right down into our upper atmosphere.
And that brings us to our third and final ingredient, the collision. This is the grand finale. This is the moment where all that energy from the sun finally meets the gases in our own atmosphere, and that's what creates the spectacular display we've all been waiting to see.
It's actually a pretty simple 3-step process when you break it down. Step 1, those solar particles we talked about, they get funneled down and plunge into the top of our atmosphere. Step 2, they literally smash into atoms of oxygen and nitrogen. Now this collision transfers a ton of energy, and it gets those atoms all excited. But they can't stay that way. So for step 3, they almost instantly release that extra energy as a tiny little particle of light, a photon. Now imagine that happening billions and billions of times a second. That's the aurora.
Okay, but that brings up another question, right? Why isn't it just one big white glow? How do we get those incredible greens and reds and sometimes even purples? Well, the answer is pretty cool. It all depends on which atom gets hit and where it gets hit. Think of it like an atomic paint palette. That classic vibrant green that you see most often, that's what happens when particles hit oxygen atoms about 100 to 200 kilometers up. If they hit oxygen way higher up, where the air is thinner, you get that beautiful deep red color. And if the particles have enough punch to get even lower, they start hitting nitrogen, and that's where you get the rarer blues and pinks.
So, here's the key takeaway. The energy of the incoming particle determines the color. It's that simple. Really high-energy particles can punch deeper into the atmosphere. They reach those lower altitudes, and bam, they hit nitrogen, and we get those amazing pinks and blues. The lower-energy particles, they can't get as far, so they interact with oxygen higher up, giving us those more common greens and reds.
Okay,
This is great. We know the recipe. But how can we know when the show is actually about to start? How can you go see it? Well, it turns out we can actually forecast this space weather, almost like we forecast the weather down here on Earth.
For anyone who wants to hunt for the aurora, the magic number is the KP index. It's just a simple scale. It goes from 0 to 9, and it tells you how much geomagnetic activity is happening. Think of it as a storm rating for the aurora. The higher the KP number, the stronger the solar storm, and the better the light show is going to be.
So if you see a K-SIOP of, say, 0 to 2, that's pretty calm. Not much is going on. K-SIOP 3 to 4, now we're talking. That's active, and you'll probably get a good show up near the poles. But the real excitement starts when you hit a K-SIOP of 5 or more. That's an official geomagnetic storm, and that's when the aurora can spread out, becoming visible way, way further south than you'd normally expect.
And this is what a real forecast actually looks like. That green band you see there, that's the auroral oval. It shows where the lights are most likely to be visible directly overhead. When you get a high CAPE number, that whole band expands and could stretch down over major cities, giving millions of people a chance to see the show.
So there you have it, the whole cosmic recipe, from start to finish. Step 1, the sun shoots out the solar wind. Step 2, Earth's magnetic field acts like a giant funnel, guiding those particles to the poles. And step 3, those particles slam into our atmosphere and, poof, the sky lights up.
But here's what might be the most mind-blowing part of this whole thing. This isn't just an Earth thing. We're not that special. The same recipe works pretty much anywhere in the universe as long as you have the right ingredients.
That's right. The huge gas giants, Jupiter and Saturn, they have auroras that are way, way more powerful than anything we see here. We've seen them with spacecraft. Heck, even comets can have faint auroras as the solar wind blows past them. It's a truly universal light show.
So the next time you see one of those incredible photos of the dancing lights, you'll know exactly what you're looking at. It's not magic, it's the story of an epic journey. A 93 million mile trip from a star, guided by our planet's invisible shield, all ending in one final, brilliant collision high up in our atmosphere. So now that you know the secret recipe, are you ready to go hunt for the lights?